So these are the notes I wanted to give to you on Friday, but the printer wasn't working. So I apologize for that, but here is what we discussed in class and on the slides. This handout, by the way, is a PDF in Schoology. This video will also be found linked in Schoology and by email. So standard position, put the tail at the origin, and once you're in standard position, the change in X and the change in Y become the actual name in component form. But we also can find the magnitude and the direction. So sometimes we use sort of an R theta magnitude direction way of describing the thing. I didn't actually plug these things into the calculator, but you can do that. Writing any vector, change in X, change in Y, they can point in any direction, and so make sure you're paying attention to your signs. The signs matter in the name. To go from 3 to 6, we added 3, so a positive 3. To go from 5 to 3, we subtracted 2. So make sure you're paying attention whether you're going left and right for X, positive or negative, and up or down for Y, positive or negative. This was the problem that I did for you on the slides, so you should have this in your handwritten notes already. So we further discussed adding vectors near the end of class, but these notes should be helpful to you. The first one being, so operations with vectors, being multiplying a vector by a number. You distribute it through. So k times a vector, where k is just a number, is k times the x and k times the b. Back in geometry, we called this dilation. You did a whole unit in geometry on dilation as a transformation. And we have to give it to both to stretch it both vertically and horizontally in a uniform manner. Addition, you add the x's, you add the y's. It's very straightforward when it's in component form. Subtraction, again, subtract the x's, subtract the y's, just pay attention to which one is the actual minus. So 2c, I just took c and I doubled both parts. For a plus b, I added the x's. Negative 6 plus 1 is negative 5. 2 plus 7 is 9. For c minus b, I didn't do, but over here I did the more complex, a minus 3c, and I wrote out my work. So negative 6 minus 3, but the 3 is times negative 4, so ends up being negative 6 plus 12 to get a positive 6. Then 2 minus 3 times c's y coordinate was 5, so 3 times 5. 2 minus 15 is negative 13. So all of this math is very straightforward. Just act on the x's with x's and the y's with the y's, and then constants multiplied by vectors get distributed through. Unit vectors are the ones we discussed are on the unit circle. So all of the points on the unit circle describe unit vectors as cosine sine pairs. We also have this new notation of I and J. Since I is the pure X unit vector and J is the pure Y unit vector, we can describe everything as a sum of two vectors. The X coordinate is the cosine of theta on the unit circle, so it's cosine I. I put the I first just so I didn't have to put parentheses around cosine theta, because you don't want to pretend like the I vector is being multiplied by the angle. You need to be clear about that. So sometimes I will put the I after with a parenthesis. Sometimes I'll put the I before just to be clear. And then sine times J. If we want to stretch that unit vector to have the magnitude of V, we literally multiply the unit vector of cosine sine by the magnitude. It stretches it. The magnitude is just a number. It's a length. So we can just stretch it out. Turns out to be the trig form for everything. Now, this is your exit ticket, part 1. You must bring this to the test to get exit ticket points on the test on Friday. So please make sure you take up your paper copy on Wednesday from the sub, or print yourself a paper copy and do this page before you even get to class on Wednesday. since we already discussed all these basics. Now, the reason I wanted you to do that perhaps is because there's another handout that is the not as basics. We're going to apply vectors as well. So the rest of 5.3, the intro was on Friday, and the rest of it is on Wednesday. So here you go, applications. Bearings is the first one. Now, I want you to know that if you see something where you got letter, angle, letter, the first letter will always be your north or south, and the second letter will be your east or west. And I read this as south, face south, then turn towards the east 60 degrees. So that problem is right, where is that? Oh, there's not a picture. I don't know. It was the one that they used right here. There's not a picture for that. But north, oh yeah, no, here's the picture, sorry. Face towards the south and turn towards the east 60 degrees. It puts the angle there, which means I'm actually at an angle of negative 30, right? From our usual theta. And another example is north 30 west. So you would face north and then you turn towards the west 30 degrees. And now you're up in quadrant 2 by 30 degrees. So your angle from the origin, or from our normal definition of the positive x-axis, which is east, your angle would be whatever 90 plus 30 is, 120. There we go. So for each vector, give the quadrant bearing and the true bearing. So in this case, they were defining it from the x-axis. So the quadrant bearing says face north and turn 15 degrees to the east. Actually, that should be 5. Oops. Turn 5 degrees, because 85 is only 5 degrees from 90. My bad. Here we go. The true bearing then is, because it's always from the north, the true bearing is 5 degrees. 0, 0, 5. Up here, we have a quadrant bearing in quadrant 3 here, because our vector is pointing down and to the left. And so we would say it's south 58 degrees west. I got the 58 from 180 minus 122. I got the 122 from 212 minus 90, because I wanted to get rid of this quadrant. So do some logical reasoning with these angles to find out, for true bearing, just what is it from the north, and quadrant bearing, what is it from the nearest vertical axis, north or south. Over here we are north 24 west, or the true bearing of 336 degrees, because it wants us to go clockwise for the true bearing. Clockwise from the north. So I have myself a little key down here, and it might help you to draw that on your notes as well. So an airplane flying at a bearing of 245 degrees at that many miles per hour, what's the velocity of the plane as a vector in component form? I need to find the x and y components, specifically pointing in that direction. So since I can get from the given information, I can glean the angle that it is 205, because clockwise this way is 65 degrees past 180 degrees. So to get to the other side, I'm at 25 more degrees, right? Which means 180 plus 25 is 205. The dotted line is the angle that I'm going to use for my sine and cosine to ensure that I'm oriented correctly. Okay, so here's some more examples. I do the same thing. A little bit of reasoning to sort out what the angle should be, but then it's just r cosine theta, r sine theta, just like polar coordinates. And then here is another example about resultant force. Now, I did the example the way that they discussed doing it, where you sum the two vectors in component form. So I write each vector in component form. R cosine I plus R sine I, R cosine I plus R sine I, where the angle is specific to that vector. Now, both of these happen to have the same magnitude. They don't always. Down here, we had an 85 magnitude at a 35 degree and 120 magnitude at 140 degree. I went straight to the resultant here and just added my x's, because once I did this whole thing, I was like, well, I could figure out how to go straight to a plus b. Sure, just r cosine plus r cosine. R cosine plus r cosine, and that's my I part. R sine plus r sine is my y part. So once I got the full I and j by plugging all this into the calculator, I have a magnitude and I have an angle. Paying close attention to the fact that I'm in quadrant 2, always draw a picture. So I knew to add the 180 degrees to the negative angle that it gave me. Now I also did it over here using the law of cosines and sines just as an extra practice. But the original logic to try and find an angle inside here, I don't know if you can tell that I erased a fair bit. So it's rather tricky to figure out an angle inside some of these triangles in order to determine the other side and use these rules. The 75-degree angle up here kind of gave me fits. But anyway, if you can figure out an angle inside and two sides, this is a side angle side. I'm going to apply the law of cosines to get the magnitude, and then I can use the law of sines from there, because now I have a key to get my angle. But then I have to do a little more math, because that's just the angle inside the triangle. I need to find the angle over here, which I previously determined would be 180 minus the inside triangle angle minus the 40 degrees that my triangle is offset. So it gets a little hairy, but that's okay. You don't have to do that. Here and here, some examples. Pause the video, take notes, however you like. Resultant velocity, I did one example that this tends to be the most confusing to people because they don't give you an actual angle. Well, it heads directly across a river. So if the shore is here, it's going to go straight across, and the water is going to flow in the direction of the river. So they're perpendicular vectors. Once I read that I wanted the angle with respect to the shore, I turned my drawing so that now my river flows that way and my boat goes that way, because now my angle theta will be defined once I find this vector's angle. It'll be defined exactly from the shore like it wants to be. So also an interesting feature of this is A is just 28J. You don't have to write 0I plus 28J. You can if you want, but it's not necessary. This is a purely vertical vector. And this is 12I. The flow of the river is only in the x direction along the shore. When I added them, I could just say 12I plus 28J. It was very easy to add those perpendicular vectors that are in the same, that are aligned with my axes. So this is something I want you to work on in class. And this is your exit ticket to bring on Friday for the rest of the exit ticket points for this part. Once you've done some practice, I'm instructing the sub to give you the quiz for the last 30 minutes of class. Good luck.